Welcome back. In this lecture, I am going to discuss about surface area. It is relatively straightforward to calculate surface area. Basically, I'm going to discuss or show you how we calculate uh, the area of a part of the surface. The surface could be infinite, so we have to look for a portion or a finite domain, a portion of the surface. So I will use an example to illustrate the concept. I have earlier discussed about the parameterization of the surface. I'm assuming that you have understood how to parameterize. So surface here is given by this equation: z equals 1 plus 3x plus 2y squared. It is not necessary to perfectly visualize this surface, but just imagine that this is a surface which is not a plane, because it is y square is a quadratic. Okay, it is a quadratic surface. And then we have a triangle given by three vertices, 3 points: 0 0 0 1 and 2 1. So you have to look at the surface from the triangle. So a portion of the surface that is just above the triangle, that is what we want to calculate. So the first point first, we have to identify which part of the surface we are asked to calculate, or we want to calculate. Okay, the working rule would be that I am going to explain, or I'm interested in. That's my favorite technique of calculating the surface area. So I will parameterize. So in order to parameterize this surface, what I need is I need to find a vector function r, which is a function of two variables, and that two parameters can be any symbol. If we are using cylindrical, spherical coordinate, I think the easiest way would be if we just look at two parameters in English letters u v instead of r theta. Okay, and basically in this example we are not using cylindrical or polar coordinate. So by looking at the function, what we can say is that we can denote x just for u. Okay, so you can set the x coordinate along the parameter u and y coordinate along the parameter v. So I have a parameter domain which is x is u and y is v. Then I have z x y z, so that can be just substituted by looking at this expression. That is 1 plus 3u plus 2v square. Okay, so once I have the parameter here, the parameter domain in this case will be the same triangle, because I have intentionally set the parameters along the x and y coordinate. So the parameter domain will be the triangle with vertices 0 0, 0 1 and 2 1. Okay, so since I have now the vector function of the surface, which is the parametric form, I can differentiate this function with respect to u and with respect to v. So let's first do the differentiation. So r sub u, which is derivative of r with respect to u, for simplicity I'm going to ignore the vector sign. So whether I write arrow or not, r is a vector, just for simplicity. So the first component is u. If we differentiate with respect to u, keeping everything else as constant, so it will be 1 second component is v. So differentiate this u with respect to u. So v is a constant with respect to u, so it will be 0. Third component is 1 plus 3u plus 2v square. So its differentiation will be 3. Okay. Now we are going to differentiate with respect to v. So let's look at here. First component, second component, and third component is pretty easy. If you differentiate with respect to v, first component is 0, second component is 1, and the third component is 4v, 4 times v. Okay. So now, what is the interpretation of the derivative of r with respect to u and v? So r sub u will be a tangent to the surface in the u direction. R sub v will be a tangent to the surface in the v direction. So that's very nice. Now if we take a cross product between those two tangents, then that tangent, the cross product will be a vector normal out of the surface. So I can get a normal to the surface instead of looking at the gradient or the other way. So I can just take the cross product Ru cross Rv. Okay. So the definition of cross product or the process of cross product is we have to evaluate the determinant of a matrix. The first row of the matrix is unit vectors ijk. Second row will be the left vector r sub u, which is 1, 0, 3. The third row will be the right vector, which is of the cross product r sub b, 0, 1, 4, b. Okay, so now the cross product will be by looking at the first unit vector I, we will evaluate this cofactor. Then looking at J, we will evaluate the cofactor 1, 3, 0, 4b. Looking at K, we will evaluate this cofactor. So that's pretty easy, and we don't need to write ijk. I corresponds to the first component, J corresponds to the second component, K corresponds to the third component. So we can just write as a component. So 0 times 4b is 0 minus 3. The jth component, second component, I have a minus sign, so I will go in the reverse direction. Instead of multiplying 1 with 4b and subtracting 3 times 0, I will first multiply 3 times 0 and subtract 4b. So that will be minus 4b. Okay. Third component is just 1. 1 times 1 minus 0. So I have the cross product, which is the normal. So the surface area So there could be various other ways to calculate the surface area, but let's say if we just follow one specific rule, the parameterization, then you look at the normal vector r sub u, r sub b, take its magnitude and then integrate it in the parameter domain with respect to u and with respect to b. The result will be your surface area. Okay, so maybe first I can just evaluate the magnitude of r sub u cross r sub b. So the magnitude will be negative 3 square, negative 4v square plus 1 square du dv. Okay, that's something we can rewrite. 9 plus 16v square plus 1. So 10 plus 16v square to the power half. Now let's just try to find the limit of the domain. So if I look at the parameter domain UV, so one vertex is just 0, 0. Another one is just given 0, 1, and other one is given 2, 1, 2, 1. So let's denote A, B, C. Doesn't matter which way to go, but I'm going to do that way. So I can see that this line here can be written as U equal to 2V, because passing through origin and also to 1. So if I substitute U equal to 2, then I get B equal to 1, U equal to 0, B equal to 0. So this is a line. So I have this domain that will be between V equal to 0 and V equal to 1. And then it will be from U equal to 0 to U equal to B, U equal to 2B. Okay. So I'll put the constant limit outside, V from 0 to 1 and U from 0 to 2V. Then I will integrate 10 plus 16V square to the power half. And I have here du, dv, du, dv. Okay, let's do the integration one at a time. V from 0 to 1, and inner integral is 10 plus 16v squared to the power half is a constant with respect to u. So I will have u times 10 plus 16v squared to the power half, and evaluate from 0 to 2v, and then with respect to v. Okay. So first write down this integral 0 to 1, and u will be now 2v minus 0, which I don't need to write down, that 0, 16v squared to the power half dv. So this is something you can think of from first year calculus. We need to make a change of variable. So let's say w equals 10 plus 16v square. You can have other option, but maybe that's the best option in this case. So dw equals 32v dv. So I see here 2v dv. So I can match it there. So I can say, okay, dv divided by 16 equals 2v dv. Now I can substitute there, and if I substitute 10 plus 16v square, which I considered w, so that with w to the power half, and 2v dv is dw divided by 16. I can just write it outside. Okay. And now I like to say that, okay, so once we make this substitution or change a variable in a definite integral, it is necessary to change the limit. But the other way is that we can just calculate it as an independent integral and then return back to original variable. We don't have to change the limit. So I just ignore the limit for a moment, and I will calculate the integral without considering the limit. So w to the power half, its antiderivative will be 2 over 3 w to the power 3 over 2. Okay, so I have to put some limit, but before going to do that, I can see this is 1 by 24. Okay, and w is 10 plus 16 v square to the power 3 over 2. Now I can put the limit from 0 to 1. So 1 by 24. If I put b equal to 1, so that should be 10 plus 16 to the power 3 over 2. Don't forget that. And when I say 0, 10 to the power 3 over 2. So finally, I can do a little bit of simplification. 1 by 24, 26 to the power 3 over 2 minus 10 to the power 3 over 2. So that's my final answer. So you have seen that we can calculate the surface area by considering a parameterization of the surface. And then the parametric surface we differentiate with respect to two variables, take the cross product to get a vector out of the surface. So this is another way to get a vector out of the surface. Integrate the magnitude of the vector, that gives us the derivative. Thank you very much.